Hi, welcome back to your new lesson. This is Lakshmikanta Tiwari. In this lesson, I'm going to teach you how you can build a simple two-dimensional CNN, otherwise known as a 2D CNN for MNIST Digit recognition. So in this, I'll be showing you how you can achieve a 99% accuracy while classifying MNIST Digit recognition. So we will be basically working on digit recognizer dataset, and it is readily available at kaggle.com. And you see here the dataset you can in fact download from here itself. Otherwise you can download this dataset from the TensorFlow itself. And you see here each image have a size of the 28 cross 28 pixels, and that's mean if we multiply 28 into 28 it would be 784. And apart from that, you see here it has the total 10 classes. Of course, it's a digit recognizer, so it has 0 to 9 classes which we will be working. Okay, and it says that if we get the accuracy more than 97%, then it says that we are having actually the good accuracy. All right, so let's go ahead without wasting time, start a new video on digit recognizer. So throughout this lesson, we will be working on a Google Colab. You need to visit colab.research.google.com. A Google Colab provide a free GPU and the TPU. If you don't have a GPU on your computer, you can go ahead and log into Google Colab. Otherwise, you can definitely use your the local GPU using a Jupyter notebook. But here definitely we'll be working on a Colab notebook. So once you visit this link, then you can go ahead into the file and open here a new Python 3 notebook. So we need to we need to give here a name. So let's go ahead and give a name here, MNIST Digit. All right, and with this you can add a code cell, and with this tab you can add a text. So let's add some text and bring this to upper. And here with the hash we can give a name, build a simple 2D CNN. All right, so let's go ahead. First of all, we need to set our GPU from a runtime and change runtime type, and we are gonna use here a TPU. I have found that the TPU is much faster than a GPU. And after that we need to click here our connect, otherwise it will automatically connect. So for a Google Colab, every time when you use a TensorFlow GPU 2.0, then you need to install it every time. So you can install a current version of a GPU, current version of a TensorFlow 2.0, which is a beta version. So pip install, and here we have a TensorFlow, and then we have a GPU. All right, is equal to 2.0.0. and then here we have RC0, that's the release candidate of 0. All right, so it's kind of a beta version of TensorFlow GPU. So it will take a little time to get it installed. So once it is installed, in meantime while it is installing, let's go ahead and import some supporting libraries like NumPy, Pandas and Matplotlib. So we can do that. Import NumPy as np, and similarly we can import Pandas as pd, and then we can also import matplotlib.pyplot as plt. All right, so let it install and just wait for a few seconds to complete its installation. All right, so the TensorFlow GPU has been installed in our Google Colab notebook. Now let's go ahead and run this cell, and after that we are going to import necessary libraries from a TensorFlow. So the first of all, we need to import the keras from the TensorFlow. Although I don't think we need directly the keras, but we will be importing the sequential model and the layers from a keras. So that we can do from the TensorFlow. All right, a TensorFlow dot keras, and then import sequential. All right, and then after that we need from TensorFlow.keras.layers, and here we will be importing The first of all, we will be importing convolution 2D, conv 2D. And then after that, we will be importing max pool 2D. And then we will be importing here a dense layer. All right. And after that, we will be importing here a flattened layer. So that we will be needing at the end of the convolutional network. And after that, we will be also importing a dropout. All right. Perfect. So let's go ahead and run this cell. And now we are going to check here a TensorFlow. We need to also, I think, import a TensorFlow as a TF. So we can import a TensorFlow, import TensorFlow as TF. All right. Now let's go ahead and check a version of a TensorFlow which is installed in our computer, which you can find with the TensorFlow.version. And it says that we have a 2.0.0, which is beta version of a TensorFlow 2.0. All right, now let's go ahead and import MNIST dataset from a keras.dataset, which you can get from TensorFlow .keras the datasets, and then here we can import MNIST. All right, and after this, what we can do, MNIST dot load data. All right, so this returns the two tuple, one for training and one for testing. So this will return kind of these two tuple. So in the first tuples, we are going to store x underscore train and then y underscore train, and in second tuple, we are going to store x test and y underscore test. All right, now we have x train and y train data. So if you see here in the files, let it refresh. Okay, so it's downloading this data. In the meantime, while it is downloading, it might take some time to complete its download. I think it has already downloaded, so it has locally stored somewhere this data, okay, which was downloaded from this link. And after that, what we are going to do now, we are going to see some images which has been downloaded. All right, so you can say those you can see those images by calling looping it for a for loop for I in range of 9. Okay, and then I'm going to plot few images, and in fact I'm just going to plot just a single image instead of so many images, and that I can say here the plt dot imso, right? So this will show the image. It takes the input. So here let's say we have the X train, the very first image that is available at 0th location, and you can see that image is here. All right, this is a 5, and similarly you can see the second image as well, which is 0, and the third image as well. So with this way you can see all the images which is stored into MNIST data set. All right, now after this, what we are going to do, we are going to see a shape of X train and Y train. So you see here X train dot shape, and this has a 60,000 images which is available for training, and similarly if you see here X test dot shape, that is 10,000 images available for a testing. All right, and the shape of each of these images are 28 cross 28. That's mean this is just a single dimensional array, and which have the 28 cross 28. Okay. Now what happens, the values between these images are quite high, and if you see the X train underscore X underscore train, and if you print this, the middle values are not being shown. So what we can do, X train and then dot max. So let's go ahead and see the max value between X train. So that is the 255. So this is quite large value. We need to bring these values in between 0 to 1 so that we can train our network in a faster way. Let's go ahead and add first few and the default cell. Now I'm going to do X train is equal to X underscore train divided by 255.0. That's mean it should be a floating value instead of just an integer value. Otherwise 0 and the 1 only will be stored. And then here we need to do for X test as well. So for X test we have X underscore test divided by 255.0. Now the maximum values of X train and X test has came to 1. So the X test and X train is having a value that is somewhere in between 0 and 1. Now this is a perfect data set available for a training of a model. So let's go ahead, and we need to also change the shape of our the training and the testing data set. Since convolutional neural network expect the 3-dimensional input, okay, the 2D, although this is the 2D CNN, but it accepts some kind of the 3-dimensional input. So what we need to do, we need to make it 28 cross 28 cross 1. Okay, and to do that, what we can do, X underscore train is equal to X underscore train dot reshape. And in which reshape we are going to make it? The reshape for a training data set, we have 60,000, okay, and then 28 cross 28 and then cross 1. So this is for X train, and similarly for X test we have X underscore test dot reshape, and here we have 10,000 and then 28 cross 1. Alright, so all the images are in between 28 into 28 cross 1. So this is kind of, now it has become, each image has become a 3-dimensional, which you can get like calling X train and the 0th location dot shape. So you see it is returning a kind of a 3-dimensional, although this is just in 2D, but we have added the 3rd dimension as well. So what should be the input size for our neural network? The input shape is the shape of this, okay, so which is X underscore train and then at the 0th location, and then here we have shape. So this is input shape for us. Now let's go ahead and start building model. So we need to first build a sequential model, and then we will start adding a layer in the sequential model. Okay, so we have got here a model, sequential model. Now we are going to add a first 2-dimensional network here, a 2D, the 2D convolution. So first we need to call here conv2D, and this takes a lot of the input, and those input you see the number of filters, so how many filters it want. And first we are going to pass 32 filters. And what should be the filter size? If you don't know these terms, then you can go ahead and visit my previous videos. There I have explained what is the kernel size and the filter. So here we have a filter size, by which filter size it will be the scanning the document, it will be scanning the digits. So that filter size we have a 3 cross 3. Let's go ahead and bring it to yes, so here we have a filter size. And after this we have activation function. So what should be the activation function? The very widely used activation function is ReLU activation function. And for a first input layer of convolutional neural network, we need to provide input shape, and after that we don't need to provide an input shape. So here we need to provide input shape. Input shape is equal to, already we have provided input shape in a variable of input shape. So this says that the first layer of the convolution has been added into a model. Now we are going to add the another layer. So with this we have a model dot add, and then here we have a conv2D, and this in this convolutional 2D we are going to add a 64 filters, and the kernel size which we are going to provide a 3 cross 3. Alright, and then after we are going to provide here the activation function which is ReLU. And then here we have model dot add. Then we are going to actually the max pool, since the parameters of this model is has increased drastically, and if you know how much parameters we have got, then you can simply run this, and at the end of this you can print the summary of the model. Sorry. So here we have a summary of model. You see the parameters has increased to 18,000. So what we are going to do here, we are going to max pool. So after a max pool, summary will the parameters will decrease to, okay. So what we are going to do here, we are going to add a max pool. So here we have a max pool 2D, the two-dimensional max pooling, and the pool size we are going to provide here 2 cross 2. Okay, all right, so let's go ahead and run this and then see a parameters. So now you see a parameter. So max pool, what it did, it has reduced the dimensions. Okay, so initially the dimension was 24 cross 24, now it becomes 12 cross 12. So the overall digit dimension has been decreased by twofold. All right, I mean the vectors, feature vectors has been reduced by a twofold. Now after this max pool layer, we are going to add a dropout. Okay, so here we have the model dot dropout. So we add a dropout to regularize our the neural network, and also to avoid the overfitting. So in fact, regularization means avoiding of overfitting, where we are going to provide 0.25% of a dropout. That means the 25% of neurons randomly will be dropped while moving to a next layer. Now after this, we are going to just provide a flattening layer. All right, so let's go ahead and flatten it. So we have added just 2 layers of convolutional neural network, and after that I am going to convert the two-dimensional data into a vector actually, and that can be done by calling a flatten layer. Okay, so here we always need to call a flatten layer in convolutional neural network. So after this, a flattening has been done. Now we are going to call the dense layer, which is also known as a fully connected layer, which is model dot add. Then we have here a dense layer, and inside a dense layer it asks how many units do you want. So the first I'm going to provide 128 units, and it also asks about the activation function. So activation function would be the ReLU. This is most widely used activation function. Then I'm going to again add a dropout here, and now I'm going to drop the 50% neurons randomly. And after this dense layer, I'm going to add a final output layer, and that can be added with the model dot add and then the dense layer. And with this, I'm going to provide here the 10 output layer, and after that I'm going to provide here the activation function. Okay, the activation function, it is a softmax activation function. All right, so you see here the difference in activation function, because the softmax activation function we use in the output layer, but in internal hidden layers we always use a ReLU function. So ReLU activation function performs better than the other functions like tanh and other kind of functions. Now here we have a softmax. After that we have our model. This is complete model. You can see a summary of this model. All right, so there are total 1 million of parameters, more than 1 million of a parameter. Now let's go ahead and compile this model. So that we can do with model.compile, and there we are going to provide here loss. A loss function is we are going to provide here a sparse categorical entropy, sparse categorical cross entropy. And after this I'm going to pass here optimizer. The optimizer is equal to Adam optimizer, that is stochastic gradient optimizer, and then here the metrics on which this model will be evaluated, I'm going to provide accuracy. All right, so let's go ahead and compile this model. Now the model has been compiled. The final step, which is most exciting, this step, which is a model training. So that we can call with the model.fit, and in this we need to provide the training and the testing data set. So here we have X train and then finally Y train. After that we are going to run it into a batch sizes, and here I'm going to say that take a 28 digits at a time to for training this model, and I'm going to train this for the total number of 10 epochs. And after that I'm going to say that the keep verbose on, that's mean keep showing the log while training the model, and then in meantime I'm also going to provide a validation data, and that validation data is the x test and the y test. So which is x underscore test, and then here we have y underscore test. So these data will be used for a training purpose, and these data will be used for a validation purpose, so that our model can fine tune the parameters, I mean the weights of this model. And it returns the iteration, I mean accuracy and the losses of a training and the validation data set, and it will be stored into a history. And after that, once it is trained, then we will be using a history to plot a learning curve of this model. So let's go ahead and run this. It will take some time to complete its training. Now you can see it has started a training, and here you see a training accuracy. Once training for a single epoch is done, then it will use the same model to test on a validation data set, and then accordingly it will find out the correct it will actually make the changes into the weights of a neural network to achieve a higher accuracy. That is also known as a back propagation. So let's go ahead and wait for some time to complete its training. Alright, so the training has been completed, and we have got here a whopping, a fantastic validation accuracy, which is a 99.21% accurate. Okay, and this accuracy, we can say it's a quite good accuracy, and the record of these accuracy and the losses has been stored into a history. But before that, let's go ahead and evaluate this model, although we will be evaluating on the validation dataset itself, which we can do just by calling the model.evaluate, and then we can call here x test and then y underscore test. All right, so it will take a little time to complete this evaluation, and then once evaluation is done, the final the summary will be printed here. It says that it has the accuracy of 99.13, and the total and the loss is 0.028. Okay, so that's quite low loss, and we have a good accuracy, 99.13% of accuracy. Now we are going to plot a learning curve before end of this lesson. So we already have the code for a learning curve. You can go ahead and watch my previous videos in which I had taken a lesson for a learning curve. So this learning curve, a function I have written which takes a history and epochs. So you see here a history, and it has been trained for a 10 epochs. And then if you print here, let's go ahead and first print a history. What's the history? The history contains a variable which is known as a history. So which you can say a history.history. It has a accuracy, loss, validation accuracy, and validation loss. So we are going to plot these in the learning curve, and these are being plotted in these two lines: plt.plot history.history accuracy and the validation accuracy. And similarly we are getting here a plot of loss and validation loss. So let's go ahead and run this, and then here we are going to say here a plot learning curve in which we are going to pass a history. We are going to pass a history and the 10 epoch. Let's go ahead and run this, and you see here. All right, so we have got a learning curve for the accuracy as well as for loss. So you see here loss, training loss and the validation loss is almost equal, and the accuracy for training and the validation is almost equal. So in this way we can say that our model is stable, and it is neither overfitting and nor underfitting. So it is you can say a perfect model which you can apply on digit recognition, okay, on actual data of digit recognition. So this is all about in this lesson. Thank you so much for watching this video. Please do not forget to like and subscribe this channel. Bye bye. Have a nice day.